Hey there. Let's maintain and rotate an AVL tree, which is a self-balancing binary search tree. Okay. All right, so hopefully by now you've seen my other videos. If you haven't, you probably won't understand this unless you've seen other videos elsewhere. But in my previous videos, we talked about what is a binary search tree, how to make one, how to define one, how to know you're looking at one, how to build one, search, insert, remove, all the operations and time complexities. And then we talked about AVL trees, which are a self-balancing binary search tree. And we talked about what are the different types of rotations you can do, why would you rotate, how do you compute balance factors, how do you know when it's time to rotate, how do you do the rotation, stuff like that. So this is just going to be one example tree, and we're just going to try to burn through it. If you want to learn more about AVL trees, see my previous videos. Okay, so supposing now that you have a tree that looks like this, let's confirm that this is a valid AVL tree. This seems to be a tree. It's a connected graph. It's got no cycles. It's a rooted tree. It's a binary tree. There are no more than 2 children per every single node. And the data is in order. So 14, 22, 36, 41, 48, 55, 65. So this is a valid binary search tree. Now to determine if it's a valid AVL tree, we just have to compute balance factors. So in my previous videos, we talked about doing this. So I'm just going to try to burn through this quickly. I'm going to put zeros on all the leaves because that's pretty easy. This 48 gets a 1. The 65 actually gets a 2. So at this point already we know there's something wrong with our tree. We need to rotate it. This is not a valid AVL tree because we see a balance factor that is worse than, plus or minus 1. So the 41 is going to have a balance factor of, let's see, just a 1. And so really the only thing that we need to rotate is going to be this 65 node. This is the node that's out of whack. Sometimes you see, the bad balance factor in other areas of the tree, maybe like a little bit higher and also a little bit lower. You want to rotate as low as possible first because sometimes when you rotate low, it fixes stuff that's higher. This is actually only true if the thing that you're rotating is a direct descendant, not necessarily a direct child, but just a descendant of the thing that you see that is higher. If you have 2 different nodes that are unrelated in terms of, they're not direct descendants or ancestors of one another, they're sort of like siblings or cousins, then it doesn't really matter so much which one you rotate first because they're not really going to affect each other. But in this case, if we rotate, starting with this 65, there's a chance that the 41 will get fixed up a little bit. I haven't tried this yet, so I don't know for sure, but I have a feeling it might. Let's see what happens. So we know that the first node that is out of balance we'll call the Z node. So I'm just going to put a Z here. Let me just duplicate this and we'll say Z. Hang on a second, I got some dashes in my pen. There we go. We'll make this the Z node. And then we have to find X and Y. We'll do that backwards. We'll find the Y first and then the X. We find them by going down one level at a time. So the Y node will be a child of Z, and we'll have to find the child that has the taller subtree. In this case, there's no choice because there's no subtree on the right side of 65. So we can only go left, but just keep in mind, if there was a subtree, let's say like that, then we would still go to the left and select that 48 as the Y node. Let me just write down Y node here because it would have a taller subtree. Notice the left subtree in this little example has a height of 2 and the right subtree has a height of 1. So let's just get rid of that little extra thing. Same thing for the X. We want to find a child of Y and we'll always take the taller subtree. So, if there was a subtree over here and maybe like another node down there, then we would still go to the right to get the 55 because it would have the taller subtree. In this case, there's only one choice. So the X node is just going to be this 55, and that's it. So let me just put an X right here. So now that we know which nodes are X and Y and Z, I'm just going to write that down real fast. X equals 55. I'm going to probably change the color here. Y is equal to 48. Z is equal to 65. And then we want to make an in-order representation of X, Y, Z and just call it A, B, C. So I'm going to say A is equal to something, B is equal to something, and so is C. So A is going to be the least value, the value that belongs on the left, because again, these are supposed to have ordered data like binary search trees. So I'm going to put 48 here and 55 there, and then 65 here. Now ABC is the in-order representation of X, Y, Z. Now that we've done that, I'm going to draw our target pattern here. So let's see. I'm going to do a tri-node subtree. Just kind of very quickly going to draw it over here, and then connect with some blue lines, because that's just like such a cool connection. Hang on a second. I put that a little bit too far down. Okay, so we'll do that, and then I'm going to do another connected line. Okay, I had to make a little edit there. So I'm going to just continue making this blue line. So I'm going to do this. And I have to update the values now. So this 14 on the left, that should be the A node. So we're going to see 48. And then the new parent is going to be 55. And then the right child is going to be 65. Always, after you fill in these values, ask yourself, have I actually drawn a valid binary search tree? If you haven't, meaning if the data is out of order in some way, then you haven't drawn a valid binary search tree, and you probably need to try again. So we've got 48 and 55 and 60. The next thing we should take into account is, are there any children that are unaccounted for in terms of the input nodes to the pattern that we've just drawn down here, the output pattern? So let me just kind of remind you that there could have been, potentially some nodes, right? Like we could have had a right child of 65, we could have had a left child of 48, and we could have had two children of 55. So there's always a potential for 4 nodes that are unaccounted for. We'll just check them one by one real fast here. So we'll say, look at the 48 first. The 48 had a right child of 55, but that's already taken care of in the output pattern, so we don't have to worry about that. Now we look at the 55. We could go XYZ if we wanted to, but I like looking at the output pattern. 55 had no children, so that's fine. And then we look at the 65. The 65 had a left child of 48, but that's already in the output pattern. So at this point, all children are accounted for. We don't really need to do that much. If there were any children that were unaccounted for, they would need to be attached under the 48 and 65 somewhere, and each child would only go in one place without, there's only one place that the child could go without invalidating the binary search tree. But I'm going to make a harder example in the next video. So now that we've done this, we're ready to reattach. All the nodes are accounted for that we're about to remove from the diagram. We're not actually going to be deleting nodes or creating nodes or anything like that. In the code, we're really just disconnecting pointers and reattaching them. So I'm going to just erase this from the diagram, but keeping in mind that the nodes are not really being recreated. And I'll just put the 55 over here, where the old tri-node subtree was. And then I'm going to recompute the balance factors for all of the nodes involved. So, I just moved the 65. That was one in the output pattern, so I'm going to put a 0. 48 also 0 because they're leaves. The 55, it's a 0. It's perfectly balanced. That's pretty sweet. And now that we're done with the nodes that we touched, we have to work our way up to the root node. We don't have to worry about anything over here on the left, because those nodes couldn't possibly be affected by the rotation we just did, because only nodes that are above the rotation will be affected. So the last one we looked at was this 55. So I'm just basically going to say, all right, 55, let's look up one more parent. It's going to be the root node, the 41. So what's the new balance factor of the 41 node? It's actually going to be better. It's going to be a 0. So with that in mind, we've actually created a perfectly balanced binary search tree. This is definitely a log time tree. Super, super fast and super, super cool. And what type of rotation did we actually end up performing? Let's see. Let me go back a slide here. So we had X, Y, Z. If you don't have the rotations memorized, keep in mind my previous videos explain all of that with some fun ways to help you remember, hopefully. Maybe some unfun ways. So I'll just kind of like reiterate real fast here. There are 2 nodes that need to be moved into position. Notice how 55 is supposed to be the new parent node, which means the 65 needs to be rotated under the 55, and so does the 48. So the 48 and the 65 both are going to be rotated into position. That means 2 nodes are rotated, which means it's a double rotation, not a single rotation. Which node was rotated first? I always rotate the Z node first, the node on the very top. And so I'll just use the rotation direction of that Z node. So that's that's a regular clockwise rotation, and that's a right rotation. So this is a double right rotation. Another thing you can do to remember is if you go from Y to Z, you're going up and to the right. So that's a right rotation. You could also imagine that there is some negative space kind of sitting here on the right side, a little right pocket, so that's a right rotation. And I'm sure there were some other ways that I added in the other video, but I can no longer remember them. So I'll just move on. We'll say we did a double right rotation in order to get this, this perfectly balanced binary search tree. So I'm going to cut the video here. In the next video, we're going to, I think, probably rotate a linear tree. You can kind of see I've already started to draw one here. In the next video, we're going to look at this like giant, gnarly linear tree, and we're going to pretend that we have the AVL rotating disabled for a while we built this tree, and then all at once we're going to turn it on and do like a whole bunch of rotations and see what the tree is going to end up looking like. It's going to be pretty ugly and fun. Anyway, thank you so much for watching this video. I hope you learned a little bit of stuff and you had a little bit of fun. I'll see you in a moment, hopefully. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all. Hello there. Hi there. Hi there. Let's maintain a self-balancing AVL tree, which is recursive. Hello there. Let's